Power conversion is everywhere, doing important work behind the scenes to generate the AC and DC voltages we use every day. Inside our homes, converting AC to DC, on top of our homes, converting DC to AC, in our cars, converting DC to DC, even when we work and when we play. Every conversion wastes power, therefore optimizing power conversion to minimize these losses is vitally important. Joining us today is CJ Waters, Technical Marketing Engineer with OnSEMI's Power Solutions Group, to discuss efficient high-power conversion. Welcome, CJ. Today on Tech Chat, we've got CJ Waters, the Technical Marketing Engineer with OnSEMI's Power Solutions Group. Today he's going to discuss high-power conversion with us. Welcome, CJ.
Hi, Dale. Thank you. Thank you for having me, and I appreciate you taking the time to kind of talk with me about OnSEMI solutions.
Great. Yeah, you got a lot of great content for us today. So let's jump right in. So to get us started, give us some context on the applications and solutions you're going to be discussing today. What power levels are we talking about as high power?
Yeah, we're talking high power applications such as, power supplies, AC to DC supplies are a big part of power supplies, especially in the high power area. Also, kind of some key applications is EVC charging. That's really big right now, obviously, with the move towards electric cars. And then also solar power as well is a big topic as well with, trying to get clean energy. And that's a great space for the high power applications.
All right. Well, give us a feel for the importance of power conversion efficiency on a global scale.
Yeah, so power conversion is obviously really important because, when you're talking about energy consumption, the efficiency of how that power is converted can really affect how much energy is going to waste. So, for example, 20% of energy consumption in the world is by transportation. So that's a huge part of the energy consumption. But more importantly, when we're talking about OnSEMI solutions, industrial applications actually consume more than 50% of the world's energy. And then within that, 60% of that energy is consumed by electric motors. So obviously, we're talking a large percentage of the world's energy. And when we can improve the efficiency of how that energy is consumed, we can really, reduce the amount of power that is consumed and hopefully reduce the amount that's wasted as well.
Yeah, and all that power wasted in conversion means heat. And so then that excess heat means more cooling and more power is wasted.
Yes, exactly.
Power conversion is often hidden all around us, isn't it?
Yeah, absolutely. There's a lot of different applications that you don't really think of when you think power conversion. Obviously, as I mentioned earlier, there's the common ones for the high power application, but it's also seen in low and mid power applications as well. A lot of consumer products and computing products, such as smaller electronics, phones and devices like that, or laptops. Or, in the mid power, you have the bigger PC applications are very common now is gaming. And of course, your TVs. And then also there's a lot of different applications. I mentioned EV charging earlier. So that's, industrial and automotive, same with solar power. But there's also a lot of different applications for, medical and lighting. Again, so just reiterating that power conversion is everywhere. And it's, kind of everywhere around us, especially in this time of all electronics.
Yeah, most of us are pretty familiar with taking the 120 volts AC out of our wall and down converting to like 5 volt DC for USB charging. But DC to DC conversion is becoming increasingly important. Automotive is an example. And then DC to AC, we see that a lot more now with all the household solar installations, right?
Yeah, absolutely. So I'll touch more on that later, but essentially you have those solar panels charging some sort of battery energy storage system in the home. And it stores that as a DC, and then it actually takes that from DC back to AC to, like you said, use that 120 volt AC everywhere in your home.
Okay, give us a high-level overview of what's important when we think about different power conversion methodologies.
So there's a lot of different applications, as mentioned, with the power conversion. And within those applications, there's different types of switching topologies that are used. I'll touch more on that later. But essentially, there's either going to be hard switching or soft switching. And so with the hard switching, the common topologies used are either PFC or totem pole. And what's important when using those is, high efficiency, making sure that their reverse recovery charge is going to be lower. And then just really trying to minimize the switching losses when you're doing that hard switching. And then the other type, soft switching, is commonly seen as a LLC topology or a ZVS topology. As you mentioned, there's a lot of DC to DC, so that's kind of commonly used there. When doing the soft switching, again, efficiency is important, but you're really trying to make sure that you don't have a lot of overshoot in that. So in regards to both of these switching topologies, OnSEMI has solutions for both of them. We have a lot of solutions, especially with our high voltage MOSFETs. And in regards to our high voltage MOSFETs, we have different versions that are optimized for whatever type of switching is happening. We have fast versions, which are great for the hard switching applications. And then we have fast recovery FETs, which are more optimized for the soft switching, again, to really focus on not having that overshoot and optimizing the recovery there.
So for those of us engineers who don't live and breathe in the power conversion world, what's the difference between hard switching and soft switching?
Yeah, most commonly a hard switch is going to be when it's going from essentially zero voltage to fully on. So it's going basically, commonly said 0 to 100. So it's starting with that zero voltage and then going all the way on, versus the soft switching. It's switching from its full power to not completely to zero. There's not a graph representing the soft switching, but on the hard switching, you can kind of see the small graph in the orange where it's going from full to the zero. So that's the main difference. Hard switching, that's why efficiency is going to be more important, because you're all of a sudden going from nothing to full power. So that's where efficiency is going to be key.
Oh, that helps a lot. Thank you. So with that, there's a lot of topologies, as you've kind of talked about.
So as I mentioned, there's the hard and soft switching, but for both these different switching topologies, there's numerous different options as seen on slide 5. The common ones are buck, boost, push, pull. Those are talked about a lot of the times. The most common one for the hard switching is going to be the flyback, and that's important because it's kind of a combo of the buck boost, and it's just really one of the more common topologies used in the different power supply applications. And then when talking about the soft switching applications, we have the LLC ZVS, as I mentioned before, and that's going to be also, it's for soft switching, but it's great for high powered applications as well. And what's important to note for all of these different topologies, there's power switchers required in all of them. No matter however you design it, there's still going to be the need for power switches. So that's why OnSEMI really focuses on these high powered applications. We have a lot of solutions to fit in with these topologies.
Now, give us some guidelines in what topologies might be a good fit in different power domains.
Yeah, so you can see here in slide 6, as I mentioned, there's a lot of different topologies. It's really going to depend on what the designer wants to use. But this is just kind of a good high level look at which topologies are going to fit into the different power levels. So as I mentioned, buck is one of the more common ones. That's kind of lower power, under 25 watts. Then you get into the flyback, which isn't going to be the most efficient, but it's great for covering the 25 watt to 200 watt range. As I mentioned, it's limited in its efficiency, but it's really commonly used in applications like laptops or smartphones and some of the white good appliances. And then moving on into the higher power, you get the buck. That's moving up towards 1 kilowatt, 3 kilowatt. That's going to be a little more efficient. And then when you're really wanting that peak efficiency for the higher power applications, the bridgeless PFC is a great option because it doesn't have that input rectifier bridge, and that's going to have more efficiency there. And then finally, when you get into the really high power applications, greater than 10 kilowatts, and as I mentioned, efficiency is really important when you're dealing with that much power. That's where you're going to see topologies such as the Vienna, triphase bridge, and multi-level topologies. So that could be either I-type or T-type NPCs, which I'll talk more on some of that later. But yeah, again, it really just depends on what the designer is looking for. But there's a lot of great options depending on your power range and efficiency that you're trying to achieve.
Yeah, and those kind of charts are really helpful for people getting started to get an idea of what converter topology may be the right fit for the power domain.
Absolutely.
Just as with these different topologies, you've got a lot of choices for the power switch technology behind them. Is that right?
Yeah, absolutely. So OnSEMI has a lot of solutions for the different power switches. You can see in this chart kind of how all the power switches compare against each other. So, of course, most commonly you can see in the blue is the silicon MOSFET, and then as well as in the orange, the IGBTs. So those two have been obviously been around forever. They've been great. They've been used in so many different applications. So IGBTs, for example, they're great because they're going to be scaled for the high voltage and high power applications. But kind of the downfall there is they don't necessarily work as well at the higher switching frequencies, which leads into switching losses. So then, kind of comparing into that, you have the silicon MOSFET. You can see that it carries into a little bit higher frequency, so it's going to have some better efficiency. Better switching performance there. But you can see that it doesn't cover quite as high of a power level. And that's where we get into the silicon carbide. That's why it's kind of the talk of the town right now, is because it kind of is a mix between IGBTs and silicon, where it can cover those high voltage, high power applications, but at the same time, it's able to really handle the high switching frequency well. And it just has great thermal performance in there and great efficiency. So that's why it's really, really popular in these high power applications. And then lastly, you get into GaN for gallium nitride. That's still kind of emerging in the market. It's being evaluated more and more. From OnSEMI side, it's currently mainly in the research and development portion. But of course, it's another wide bandgap technology that we're exploring right now, and hopefully we'll be developing more and more moving forward.
Yeah, the growth in silicon carbide has been pretty remarkable. I saw a recent estimate that it expected to double again over the next 5 years.
Yeah, I believe that. There's more and more articles about it everywhere lately. So OnSEMI had big news as well that we're going to be acquiring a silicon carbide company as well. So obviously really important from the OnSEMI side to be moving forward into that market.
Right. Okay, you've been walking us down from the high-level issues to some topologies and FET types. Let's dive into some circuit design, and so us EEs can start geeking out by discussing schematics.
Great. Yeah. So we're taking a look at the typical AC to DC MOSFET block diagram. This is kind of what you commonly see in the power supply designs. So moving from left to right, you have the AC input going into a PFC, whether it's a boost or a bridgeless or a half bridge. In this case, we're using a boost PFC. So again, I talked about all those topologies earlier. You can use anything depending on your design. So here we have the boost PFC, and this is commonly where you're going to see the 650 volt super junction MOSFETs. That's kind of our main technology that we'll see used there from OnSEMI. And that's, we have the super junction MOSFET, which is just our silicon MOSFETs. That's what's commonly used. But as we move into the silicon carbide space, we have options there as well. And we have a lot of different package options there. I'll talk more about our technology later. So then moving to the right, you can see there is the rectifier diode. And that's, again, in the past, if that was a diode, that'd be what we call our ultra-fast diode. That's just a silicon diode. But again, moving into the silicon carbide space, as you have these technologies that can really handle high power and high frequency, silicon carbide is a great fit there as well. And then as you get into the primary side, that's kind of where, again, you're going to see our super junction MOSFETs or the silicon carbide, typically from 600 to 650 volts. But the focus there is going to be that soft switching that I mentioned earlier. So you can see you kind of have, your LLC design there, your LLC topology, excuse me. And that's, if we're using our silicon technology, that's our fast recovery MOSFETs. And then finally, as you get into the secondary side, historically, it's diodes that have been used there. But since, efficiency, again, is the focus here, it's transitioned to MOSFETs being placed there. So specifically in the secondary side, you're going to be mainly using medium voltage MOSFETs, which is typically from 40 volts to about 200 volts. And so OnSEMI has a lot of great technology and solutions to offer there for those medium voltage. And then as you finish through the circuit, finishing on the right, the DC output then goes into the other point of loads, and then wherever the end consumer is having that power run to, whatever application, it finally reaches there after going through that power supply block.
So the new technologies in FETs are also allowing you to do some more efficient topologies for the high performance switching, correct?
Yeah, absolutely. So when you combine that new technology with different topologies, so here in the PFC, we're using a totem pole, where in the previous one, it had been a boost. And a couple slides back, I showed that the totem pole is going to be one of the more efficient ones. So when you combine that with the new wide bandgap technology, you really maximize your efficiency in the power supply application. And some of the higher power applications where this would be seen is either cloud servers or telecom applications, where you really need a lot of reliability, efficiency, and then of course you need it to cover that really high power level.
And this is an example where we see that, not only you have to pick the right topology, but moving left to right here, you've got different FET technologies to really achieve that high power conversion efficiency, and much better than what you get with a single technology.
Absolutely, yeah. As I mentioned, OnSEMI has a lot of solutions for it. We have your classic silicon MOSFETs, silicon carbide, and then our medium voltage MOSFETs as well. And we're working on researching GaN. So really trying to cover all the bases there, and offer full solutions for the entire design. This is a great reference table to kind of wrap up the different topologies that I've been talking about. Showed it in a real high level graph earlier, but this is a little more detailed on the actual power levels that they can be used, as well as the applications where they're seen. So you can see, as I mentioned, flyback is real common. You can see in the table that there's different types of flybacks as well, and for different current levels for all those different voltages. So won't talk too much into detail. You'll be able to see this table, but again, in the bottom left, you can see just real high level. Flyback is great from 5 watts to 120 watts, commonly used in laptops, smartphones, some smaller white good appliances. And then you see the LLC, which is the soft switching that I've talked about. That's great for 120 watts to above 2 kilowatts. That's going to be bigger computing and consumer devices, TVs, higher powered PCs, again, different white good applications. So a lot of coverage there. And then lastly, PFC is really going to be focused on that real high power level from 75 watts to above 1 kilowatt. That's really going to be the bigger white good applications, as well as more high power, such as server, different industrial and automotive applications, and HVAC as well. So just kind of a great way to wrap up where the different topologies fit, their different power levels, and how they compare against each other.
Yeah, this is a great reference. I can imagine engineers taking screenshots of this slide as they're listening to this chat.
I sure hope so.
Right. Okay, CJ, what do you have for us next in the area of applications?
OnSEMI, I just really want to hammer home that OnSEMI is a great partner for your different fast DC EV charging solutions. I talked before that electric vehicles are really emerging right now. They're obviously growing more and more. And the main question around them is, how do we quickly charge those vehicles to continue driving them wherever we need to go? So we're really focusing in this application. OnSEMI has a lot of years of focused expertise specifically for this. And then with our website, we have a lot of powerful online tools. And then we also have evaluation boards that customers can order to try with their design and make sure that we're hitting the specifications that they need. And then on top of that, we just really have an extensive portfolio of countless options for those designs. So if one part's not working, we definitely have a replacement or alternative option as well. And then on top of that, not counting all the solutions that we have to offer, OnSEMI also has its own supply chain to support the manufacturing of its products from start to finish. So that allows us to kind of control, the process more, hopefully control the availability of the supply, as well as some of the costs as well.
Yeah, making these high efficiency conversion systems takes more than just good power switching transistor technology. The packaging, the module design are also super important. And so it's going to be nice to come to kind of a one-stop shop.
Absolutely, yeah. As I move into some of these application block diagrams moving forward, you'll see that we really try to offer the whole solution, as you said, a one-stop shop, and just really offer quality parts all around that can fit your entire solution.
Now, EV charging systems are a whole lot more complex than a standard wall plug, aren't they?
Absolutely, yeah. So in your standard wall plugs, those are going to be called either level one or level two EV chargers. These are typically what is seen in the home. They plug into the level one plugs into the 120 volt outlet, or the level two plugs into the 240 volt outlet. But what I really want to talk about is the level three DC fast chargers, or the fast EV chargers. This is going to need a lot more power. These typically, if you do get one installed in your home, you need a special installation, special kind of power requirement for it. But yeah, this is really important for the electric vehicles because it allows those customers to get the fast charge that they're looking for. So, with typical combustion engines, you can pull into a gas station and fill up in a couple minutes, but that's not quite as convenient for these lower level one and level two chargers. They need to charge in the garage all night. But with the fast EV chargers, they're looking at times of less than an hour that you can fully charge your car and continue on with your drive. So that's really awesome when we're talking about the electric vehicles. And so in this application and in this market, power density is going to be the key here. How much power can you have flowing through at one time to charge that battery as fast as possible? And with that, when we're talking about high power density, silicon carbide is going to be the first choice for that. Silicon carbide is great because it really handles that high power density and has thermal performance that is really superior to silicon when it is taking that much power. So, as I mentioned, the more power density means the faster that you can charge the car. So, really trying to focus on silicon carbide devices in this market. And in this block diagram, you can kind of see the different aspects of the design for these EV chargers. So, OnSEMI has a lot of the different solutions shown here. We have current sense amplifiers. We have the devices for your three-phase PFC. We have the gate drivers for those power switch devices, different voltage sensing solutions. And then we also have the isolation technology as well to make sure that, there's no issues with protection there. So just to wrap it all up, OnSEMI has a lot of solutions to cover this whole entire application. I'll touch more on the individual products that we have later, but just want to really hammer home that OnSEMI is really focusing to offer as much support as we can for these fast EV chargers. Another important application with these high power designs is energy storage. So that can be either residential energy storage, which is seen here on slide 15, or it can be commercial energy storage. So shown here, we have a solar panel option as well to power the home. That's not always going to be the case, but it's good to show here all the different options that can take place in these residential areas. So here you can see that there is both an AC input coming in from the power grid, and then we also have a DC input coming in from the solar panels. So what's happening here is the solar panel is feeding DC to DC into the charge storage bank, so some type of battery energy storage system inside the home. So that the solar panel supplies DC into that, and then it's able to, from that energy storage, it transfers it back out from DC to AC to be used everywhere through the home. So you can see that on the right, it's rectified from DC to AC and is used as an AC output. And then we have the power coming in from the AC as well from the power grid. That's rectified from AC to DC to go into the energy storage. And then again, it comes back out from DC to AC to be used in the rest of the home. So this is kind of tricky because of course, it would be ideal to only use the solar panel, but unfortunately, there's no sun at night. So that's kind of called the off-peak hours where you're not having any solar power. So essentially what happens with solar power is during the peak sun hours during the day, it takes that DC power into the energy storage and tries to charge that battery to fully charge. And then later on at night, it can use the power off of that battery if there's enough to support it throughout the night. But if this isn't the case, that's why you still have the AC from the power grid to make sure the house still has power there.
Yeah, adding local storage as part of this integrated power solution with solar panels and connected to the AC grid just makes perfect sense. And obviously you need efficient power conversion for all the different directions, DC to DC, DC to AC, AC to DC.
Yeah, absolutely.
Now let's dive in some more detail to the actual FET technologies that you have available at OnSemiconductor.
Yeah, so when talking about our strategy at OnSemi for how we want to approach the wide band gap market, which is going to be silicon carbide and gallium nitride, we have a very focused strategy of how we want to kind of proceed in the market and move through the market. So the plan from OnSemi is to be fully vertically integrated from substrate epi to the actual fabrication of packaging the devices and having ready end products. So we currently have agreements with Cree. And then, as I mentioned before, we are working on acquiring GT Advanced. So that will be big in terms of our silicon carbide supply for the wafers. So we have, contracts there, agreements there, trying to really set ourselves up to have a good supply of silicon carbide. And then another important thing with the process there is we're currently working on migrating towards the 200 millimeter wafers, which is going to be the 8-inch wafers rather than the 6-inch. This is really going to allow us to kind of increase our output and make sure we have a solid supply of silicon carbide devices. So that's exciting news there. And then in regards to our actual devices that we have for silicon carbide, we have a lot of discrete devices covering, 650 volt, 1200 volt, and 1700 volt diodes, as well as 650 volt, 900 volt, and 1200 volt MOSFETs. So that's our discrete options. We also have module options as well. So we have hybrids with IGBTs, silicon MOSFETs, and silicon carbide MOSFETs and diodes. And then we also have full silicon carbide modules that include both silicon carbide diodes and silicon carbide MOSFETs. So that really is able to just maximize the performance there. And then finishing up, we also have a lot of different support options to help the engineers, finish their design and make sure that they're getting the performance they want with our products. We have a lot of knowledge for these applications, a lot of knowledge of these silicon carbide products, and we're able to help those engineers with all their design needs.
Yeah, OnSemi's kind of taking a back to the future kind of approach with this vertically integrated OEM, having those technologies and the broad knowledge base from the substrates all the way to systems must provide you guys some unique advantages.
Yeah, it's definitely it's been great from our side. Obviously, there's supply issues everywhere, but it's great working with this new technology and really trying to be a leader in this wide band gap market.
So let's talk about that new cool kid in the transistor market, the silicon carbide.
Great. Yeah, here's a look at specifically the silicon carbide MOSFETs. These are going to be all our discrete devices. And what's really important here is that it offers superior switching and better reliability when comparing to the silicon MOSFETs. So our typical technologies are our super junction MOSFETs for the silicon, but here we have our silicon carbide, which is really just going to outperform those technologies. And these have a lot better thermal performance and current density. As I mentioned, with more current and power density, that means more power is able to flow through. In applications such as EV charging, you can charge your car a lot faster. So it's a great option for not only EV charging, it's also a great option for solar inverters, different power factor correctors, and then also power supplies as well, whether it's on uninterruptible power supplies or telecom and server power supplies. The more power that you're able to push through efficiently, the faster everything is going to be. So again, just a really incredible technology that we're working on developing and using, and it fits in great with the rest of our portfolio of products that really just allow us to sell an entire solution. And you can see that kind of on the bottom left, where we're just selling the entire solution, not just one or two products.
Yeah, there's some really exciting stuff coming on in silicon carbide. So silicon carbide is used not just for MOSFETs, correct?
That's correct. We also have silicon carbide diodes. Those are also offered as discrete devices. We have a very wide portfolio of these silicon carbide diodes. As I mentioned before, they cover 650 volts, 1200 volts, and 1700 volts. So really covering that high power level, covering all the bases there. Again, similar to the MOSFETs, you're really going to see superior switching and reliability over the typical silicon diodes. A lot of great features with these devices is that there's no reverse recovery charge. and it also has a low forward voltage. So this allows it to achieve that better efficiency. It allows it to switch at a faster frequency. It allows it to handle that increased power density to make it much faster and move power faster. And then to wrap it all up, you're with these not only silicon carbide diodes but MOSFETs as well. When you're using the silicon carbide, you're able to really minimize the board space in your design. You need a lot of less capacitors when using these devices, so it allows you to minimize the space needed in your design, which is also important. And again, these silicon carbide diodes are great for use in all the same applications as silicon carbide MOSFETs.
Yeah, and as you're kind of touching at the benefits of not just faster switching and better efficiency, but you can make things smaller, you generate less heat, and so the advantages just kind of cascade.
Absolutely, yeah.
So let's dive a little bit deeper into silicon carbide technology. Give us some insights into what is going on inside these devices that makes it so efficient.
Yeah, we can talk about how great silicon carbide is as much as we want, but it's great to see a visual representation of why it is so much better. So, in the top left, you can see that silicon carbide has a much higher dielectric breakdown versus silicon. So, essentially, what this means is that the thickness needed for moving 10 kilovolts is much smaller than what would be needed from the silicon technology. So this reduces the electrical and thermal resistance, which essentially translates to having lower power losses. So that shows why it's more efficient and has less power losses. And then in the top right, as I mentioned before, silicon carbide is able to move a lot more. It supports a lot higher power density, and that's because it has a 2 times higher electron saturation velocity when compared to silicon. So you can kind of see how much faster it's able to move those electrons. It has twice the speed when comparing to silicon, so it allows it to have those higher switching speeds that I've continued to talk about. And again, that visual of how much faster it's able to move really shows on why it's so much better. And then skipping down to the bottom right, what's really important as well is that it has a 3 times higher thermal conductivity. And this is super important because it results in lower operating temperatures and therefore less thermal stress. So ultimately, the entire design has less heat coming from this power switch. And then ultimately, with this power switch having less of the thermal stress, it really increases the reliability of the part and allows it to last a lot longer.
Yeah, and some of these benefits of silicon carbide have been known for decades, but it's really been the rise of the applications and even maybe perhaps more significantly, the improvements in the manufacturing of silicon carbide to drive down the cost that have just really come together recently to drive this explosive growth.
Yeah, definitely.
All right, let's talk about some silicon-based MOSFETs now.
Great. So when I mentioned earlier that we also have medium voltage MOSFETs as well, this is a good high level look at the portfolio options that we do have. So for our OnSEMI, we cover from 40 volts to 150 volts. And then within this medium voltage technology, we offer 3 flagship technologies. So you can see featured first is the T6 series. This is T6 stands for Trench 6. And these implement shielded gate technology, which allows the device to have dramatically reduced RDS(on). So that's great for allowing high efficiency and performance in the applications. And then similar to the T6, we have T8 or Trench 8 MOSFETs. These are more optimized for fast switching applications because they have a lower output charge and gate charge. So by having those lower charges, we achieve faster switching. And then finally, we have our PTNG, which is our power trench next generation devices. These are for 80 volts up to 150 volts. So those cover that higher voltage range within this area. These devices are tailored to have a 50% reduction in QRR and TRR compared to our competitors. So these devices are really industry leading devices and they're great for above 80 volt applications. So with all these different and with this PTNG, we achieve a very high efficiency and also have reduced spikes when using that technology. So that's the importance there. But ultimately, with all these different technology options, we have a lot of coverage for the medium voltage MOSFET range and offer a lot of solutions there.
And this is a reminder of how amazing silicon is for MOSFET technology. Is these power devices are going to look nothing like the sub 10 nanometer transistors used in our smartphones.
Definitely, yeah. A lot of evolution for these products.
And CJ, just like you provided for the converter topologies, you've got a handy chart to help designers get started in selecting a medium voltage MOSFET technology, correct?
Yeah, this is actually for a high voltage technology. So the previous slide was our medium voltage MOSFETs, but these super junction MOSFETs are going to be our high voltage, for above 650 volt. So we have also three key technologies here as well. You can see on the left, we have the easy drive versions. This is important because it has an internal gate resistor, which allows it to have reduced voltage spikes, which allows it to lower the EMI. So that's going to be great for applications where noise interference is going to be an issue. And then you also have the fast recovery FET in the middle in the orange. You can see kind of some of the devices we have there. This is great for, as I mentioned before, those power supply applications. It's our fast recovery FET is designed to have the best in class QR and TR characteristics that are going to be needed for those software switching topologies like the LOC. And it allows it to improve the overall efficiency and reliability of the system. And then lastly, we have our fast technology. This is really optimized for the high switching frequency applications, and it's designed for those hard switching topologies, as I mentioned earlier. So we have a lot of coverage with our high voltage super junction MOSFETs. And then on top of that, we also offer a lot of different package options. You can see here we have 11 different packages, both through hole and surface mount packages. So that's great. That we have it's the same story for medium voltage MOSFETs as well. I didn't show them, but we have a lot of the similar common industry packages for those devices as well. And in the bottom right, you just wrapping up, it's a great visual of how the different devices compare against each other when looking at different figures of merit and efficiency.
Yeah, it's very interesting. Packaging isn't very sexy, but there's been a lot of research and development in that area for high power applications as well, hasn't there?
Yes, absolutely, and we're also taking part of that. We continue to develop new packages. A great option that we're also developing, or have also some released, is we have dual cool packages. So these are great because it cools through both the top and bottom of the device in surface mount devices. So that's also very exciting when you're talking about that thermal performance and how that heat is dissipated.
Yeah, absolutely. So this is all really educational and certainly helping me understand a little bit more about power conversion. What's the best way for people who want to get started doing development in these kind of systems?
OnSEMI offers a lot of evaluation boards that can be used. These are all highlighted on our website along with our other support design tools. But eval boards are a great option because it allows the designer to try the actual devices and make sure they're hitting the specs they need. So in regards to our evaluation boards that we offer, OnSEMI offers a lot of different multiple EV charging eval boards specifically. So we cover the kind of common power ranges in there. So we have a 3.3 kilowatt board for both our silicon discretes and modules. And then we also have a 6.6 kilowatt board, which is developed for the onboard chargers used in electric vehicles. And this is using our silicon and silicon carbide discretes, as well as other devices, and really kind of just focusing on that onboard charger. And then we also have a 25 kilowatt board in development. This is important for the off-board EV charging stations, especially those fast EV chargers that I mentioned. We're still developing this device, or this eval board, should be releasing into this year. So that's exciting for it to be used for those EV charging station, designs. But ultimately, you can see the evaluation boards here that we have to offer, the different power ranges, which devices that they are used for, and what the different applications that they're used for. But on top of that, I just want to mention that OnSEMI is also releasing the guides with these eval boards to assist in those engineering decisions. These guides offer explanations of the boards at a much deeper level and give a better understanding of the process used for the thought behind these eval boards and how to really optimize utilizing them for the design. So Not only is it a great tool by itself, but we also offer a lot of support around it to really make it as comfortable and easy as possible when designing for these applications.
That's excellent. So not only do you have these development kits for EV charging, but you've also got some other things that help designers get started.
Absolutely, yeah. So I know we've mainly talked about power switching today and the different power switch technologies, whether it's, MOSFETs, IGBTs. Those are typically going to be the focus when talking about power conversion. But it's also important to remember that you need to have good driving solutions for those power switch devices. OnSEMI has a very wide portfolio of gate drive options to drive those power switch devices. So please go ahead and check out the website on our different gate driving solutions. But on top of that, we also have gate driver evaluation boards as well. You can see in this slide that we have a wide array of options that have been released, and we're continuing to develop and release more and more. And in regards to the different power switch technologies, we have gate drive evaluation boards for both silicon carbide MOSFETs as well as the typical silicon MOSFETs and IGBT discrete devices. And then on top of that, I mentioned somewhat that we have power modules combining the different power switch technologies. So we also have gate driving solutions for those power modules as well, and different evaluation boards to help there. So really, just to wrap it up, OnSEMI offers eval boards to make the design easier for both power switches and the driving solutions. And that's just part of us offering an entire one-stop solution for all the different design needs for engineers.
All right, CJ, thank you very much for taking time out of your busy schedule to walk us through this great introduction to high power conversion. We've covered a lot of ground today. We've done topologies, applications, transistor technologies, eval kits, and some I've probably already forgotten. So I'd encourage listeners to check out the links below for more information. Thank you, CJ.
Yep, thank you so much for having me. I'm happy to represent OnSEMI, and I hope to be hearing from some of you engineers soon and any design questions needed.
Excellent. Thank you, CJ.